today to introduce Deirdre Shoemaker. Deirdre was, I believe, the youngest surviving member of the Grand Challenge.
We killed the others? What does that mean? They died.
And Deirdre got her PhD with Richard Massner of Texas and spent some time at Cornell and then got a faculty position at Penn State where she spent quite a bit of time, and just recently she has moved to Georgia Tech, taking the southern migration, and she's going to tell us today about simplicity of binary black hole coalescence and its implications for detection.
Thanks, Mark. I think you reduced my age by a few years, and I appreciate that, actually. Well, thank you for spending time here with me today, and also maybe people in LIGO. I don't understand this whole streaming thing, but it looks interesting. I'm going to talk a little bit about some of the work we've been doing at what was formerly Penn State, now Georgia Tech Numerical Relativity Group. And I've been informed there's a typo on our website, so I apologize. We're a pretty new group. Georgia Tech actually didn't have an astronomy department. And so they started this new Center for Relativistic Astrophysics, which Pablo's the director, and there's myself and two other faculty, David Valentine and Ignacio Taboada. So we cover numerical relativity, particle astrophysics, and some high-energy astrophysics. We're very new effort since we just started in August. And we're going to have, so I have this page up as a little advertisement for our new center, and also to announce an inaugural conference we're having in May. I know most people are overcommitted at this point, but we hope to see some of you there to celebrate the new center and also to talk about sort of the mission of the center and certainly of the conference is something we're all interested in, multi-messenger astronomy. So the beautiful thing about talking to you guys is I don't have to motivate gravitational waves. We all are very comfortable with them. So of course here's some pictures of our universe in different wavelengths. And it's going to be very exciting, clearly, when gravitational waves joins this group. And who knows, you guys are probably going to be seeing these in a few years and really change the way we look at the universe. And it's exciting to even be a small part of this effort. So this is kind of a joke slide, but this is my picture of what you guys do. You have some kind of noise that looks like this red stuff. And then somewhere deep down in there is a blue signal. And I think it'd be great if that were really true, that the signal was blue and the noise was red, because it'd be a lot easier to do your job. This is a quote from a numerical relativist called Jeff Winokur. He said that he thought challenge in detecting gravitational waves was like finding a needle in a haystack, except first you need to know where the haystack is, and the needle, for all you know, looks like a piece of hay. So today I'm going to talk about one particular piece of hay, a blue piece of hay, which are binary black holes. And clearly there's tons of sources of gravitational waves. Many of you here do several of them. I'm only going to talk about binary black hole coalescence and our group's efforts on that front. But of course we've got gamma rays, and neutron stars, and supernova, and many more for both ground and space-based detectors. So the two-body problem, kind of Mark alluded to, has been a little bit infamous since probably before the Grand Challenge for binary black holes started. This is a famous picture from Kip of the inspiral merger and ring down of those two black holes. In some sense, you might think the two-body problem for black holes in general relativity should be, in some sense, the simplest, because we don't have matter terms to worry about and to understand, but of course we have the singularities from the black holes in there. And I think it was Stu Shapiro and Saltykowski who coined the term the Holy Grail of numerical relativity in 1985, calling the Holy Grail being that you had a code that could simultaneously avoid singularities, handle black holes, retain high accuracy, and run forever. And of course, the first huge major breakthrough in numerical relativity happened here when Franz Pretorius was a postdoc in 2005, when he had the first orbit merger and ring down of two black holes. Quickly followed by a couple groups, RIT and Goddard, who put together a pretty simple approach that most of the groups are now using, called the moving puncture approach. Of course, you've got the Cornell Caltech team here doing something slightly different, closer to what Pretorius does with a hyperbolic formulation. So I'm not going to talk much about this numerical relativity problem. You guys have probably heard plenty about it. I mean, surely there was a combination of things that made it work, some kind of good set of equations for Einstein's theory, a good set of coordinate conditions to handle these singularities. And I think also important, sometimes we don't talk about it enough, is our ability to do computational stuff like mesh refinement, really have well-resolved singularities in there and waves and other things. Instead, I'm going to talk about what we can do since we've had this ability to solve the binary black hole problem. And really, I think it's almost a luxurious place to be, not because we know how to get past this point, but because since we don't have matter that we don't understand in our binary black hole simulations, we really can solve the equations to sort of find out how well we can solve them. So we can truly not model the problem, but solve it from the principles of general relativity and have a sense for when we know we've done it right or wrong. So numerical relativity today, and this I'll treat as my outline for the talk, probably the single best, most impressive long-lived waveform has come out of Caltech and Cornell recently. That's their, I don't remember how many orbits that is. 16 orbits and merger. So right now, these types of waveforms, there's a lot of stuff going on in numerical relativity, but this type of information is being used, as far as I understand, mostly at the moment to test temp banks for detection. Right? So LIGO has a sense of how they're trying to get a gravitational wave detection done. And you're using waveforms like this potentially to test those temporal banks to see how well they would do at detecting a binary black hole signal, potentially to build new ones. Maybe it's hybrids where you add other information from post-Newtonian or analytic methods in with the numerical relativity information, or standalone. And a lot of people are working on motivating and testing phenomenological or analytic template banks, ones that might be based on the information from numerical relativity, but instead of using the numerical waveforms themselves, have a new waveform that's simpler to handle for detection. I want to talk a little bit about how we might expand this role a little bit. Use numerical relativity as a probe for parameter space, especially at the merger regime, where we might be able to cover more parameters from that than you can with inspiral. Probe of potentially interesting non-circular encounters, centric probably being a lot more likely, even if it's not too likely than hyperbolic, but we look at both. And we've started a new effort to provide information to burst analysis. We're right now looking at mergers with Laura Cotonati at University of Massachusetts. And potentially I'll talk about what I mean by flybys, sort of bursting from strange encounters of two black holes that do a few bursting orbits where they give off gravitational radiations and they fly back out again before they come down and merge. And I won't really talk about it, but it's kind of interesting to think about what could we not be thinking about. What could the universe have in store for us that we haven't anticipated, where numerical relativity might potentially play a role, like some of the strange Zoom world behavior people have been seeing in people like Franz Pretorius and his parabolic and hyperbolic encounters. And of course, there's stranger things that numerical relativity is up to that I'm not going to talk about. The plot on the right, the orange plot, is from Ulrich Sperhake, who's a postdoc here. And he was looking at really, really boosted black holes on a head-on collision, where he's really pushing them as far as he could, a high Lorentz factor. And Franz Pretorius has been working a little bit with the Large Hadron Collider to talk about what types of things they might see. I'm not going to talk about LISA, although clearly one of our huge future motivating factors for numerical relativity is LISA and the accuracy requirements it demands, because I guess the elephant in the room is LIGO, so most of us are fixing our attention on that at the moment. So the first summary of things that people have been doing, I put under the title of informing gravitational wave detection. Trying to get whatever information we might have in our hands right now, having looked at these binary black holes, to the gravitational wave community. Two big efforts that have been done, and I put up plots there from them. AGIF from the AEI effort, and PUN representing some Maryland and Goddard work, was to create these hybrid waveforms to try to get the best of both worlds so that you have post-Newtonian and numerical relativity working together to look for binary black holes. And also just testing these analytic and phenomenological templates. There's been other work, and actually there's some recent work by you guys, some guys here at Caltech, on testing Alessandro Bonanno's work on phenomenological templates. We've been doing work on just looking at the numerical relativity waveforms themselves and trying to understand what could they tell us about the parameter space and how likely it is to see mergers and inspirals in the regime where numerical relativity is relevant. And as I mentioned before, building banks. So I think one of the neat things that's come out recently, last week, is the final success of the Ninja project, which a lot of you in the room participated in, where it was like the first joint collaboration of numerical relativists and data analysis, combining our efforts and attempting to do, using the numerical relativity waveforms to do some injections in the data analysis routines. It wasn't a very highbrow attempt. It was just sort of a, let's see if we can do this. And I think it was successful in that. And we're going to probably do another effort to see if we can do more scientifically relevant results. So this is the worldview at Georgia Tech. Our code is called the Maya crank code. The waveform at the top was an eccentric waveform we did to compare post-Newtonian and our numerical relativity eccentric binary. It had no spin and it was equal mass, so the only parameter was eccentricity. It was about a 0.1 eccentricity or 0.2 that's up there. Our code is built off of something called Maya crank. We take Einstein's equations as a PDE and we actually send them into a Mathematica script. It's called crank. So you type in Mathematica what equations you want to solve. For us, it's something called BXSN. You turn the crank of a Mathematica script and it writes your code for you, more or less. So it's a relatively simple thing to use. It's not quite as easy as I make it out to be. But for example, we can go to lower order differencing to high order, 6th order finite differencing, and it didn't take that long, maybe about a month. We use Cactus, which is an open community code. It's built by AEI and the LSU groups to do a lot of our computational infrastructure. And we use Eric Schneider's Carpet to do our mesh refinement. And we have a lot of other tools that come in so we can analyze our waveforms. And the architects of our code were mostly Ian Hinder and Frank Herman, who were postdocs at Penn State and have now moved on. And the rest of our team, I've listed their names. So here's my personal point of view, I guess, my cartoon of what I think the binary black hole problem looks like. It starts out, right, as these two black holes with many parameters. You've got the masses of the individual black holes, the spin magnitudes, the spin orientations with respect to each other, with respect to the orbital angular momentum. And all this comes down at the end of the day to a single black hole, that's Kerr, that is described by mass and spin. So in some sense, we're going from a much more complicated system to a pretty straightforward, simple black hole. And we're interested in this entire process. So we have a pretty large parameter space we're trying to cover, especially with spin and those spin orientations. And if we're under the impression that we need information from this process and from numerical relativity to test or to form new ways of detecting gravitational waves at a minimum and potentially actually using these waveforms themselves, then we could pose the question of how do you best spend your resources and get the information we need. Because it's not, well, we're successful right now. It's not that we can all go out and cover this entire parameter space in the next few weeks at the accuracy we might want. So how do we make our choices? I have a decision structure in mind, where as numerical relativists, we choose a family of data. Maybe you want equal mass, circular templates of spin. Maybe the orientations are up and down, and you're just going to vary the magnitude. You've got to do those runs, extract those waves, and do something. Compute the matches, inject them into Ninja. We do something to determine whether those waveforms are going to be of good enough quality. I put a recent paper by Lee Lindblom with Ben Owen and Duncan Brown up there because I think it represents some things that we could actually use to determine the quality of our waveforms and whether or not they're going to be appropriate. At some point, we need input from the LSC. We're not an island standing here deciding what we think is going to be the best use for gravitational waves on both what we do with them and how we decide if they're good enough. And then decision has to be made. Are we good and ready to go and we just need a new set of parameters and a new line drawn in parameter space? Or do we have to refine this parameter set? Do we need it to be more resolution, more magnitudes? We should say hi, come in. So, maybe we had this set that's covered a certain amount of magnitudes of spin, but we really needed 10 more than what we had, that we weren't covering that little small parameter space well enough, and we'd have to go back and redo it. So I'm going to take a couple examples of forays, which is like, battling in enemy territory in a way, of parameter space. The first case I have up here are our eccentric binary black holes. They're equal mass, non-spinning. So the only thing we varied was the amount of initial eccentricity. Now, the binary black holes that we have in this code, we're setting up the initial data. So the black holes start at some separation, depending on its eccentricity, and goes through about anywhere from 2 to 10 or 20 orbits. Here's I think our longest one is probably 10 orbits for these cases. Here's two representations, an eccentricity of 0.1 and 0.3. Now, the expectation we all have is that most binary black holes will circularize before they reach LIGO band. There's been some papers out murmuring whether or not we should expect some more eccentricity. I'm not going to really weigh in on that debate. I don't really know for either the ground-based or the space-based. But in an effort we had then at Penn State, where we were using eccentric waveforms to compare to eccentric post-Newtonian, we decided to take a look at these and see what they would look like as signals for detection. I included these waveforms right here on the left to point out a very important effect of using this family of initial data where we're changing eccentricity. And that is, the higher the eccentricity we have, the fewer gravitational wave cycles that are present in our numerical waveform. And I have eccentricities up to 0.8, but at that point they're purely plunged. So one of the important differences that comes in is these number of cycles that are present in our data. The circular case is the most. I think that was the one that has 20 gravitational wave cycles. The second thing to note is this is a trajectory plot where red and blue are two different punctures, or the black holes, orbiting each other. When they're far away from each other, you can see some nice modulations here from the eccentricity, but they map onto a very simple circular pattern. So by then, we've shed all that eccentricity, and we're back to being a circular binary black hole, even in this nonlinear regime where we had a significant amount of eccentricity pumped into the system. So we had an original paper looking at, out in 2008, looking at these numerical systems. And we call them simple, and it was one of the motivations for my title because they do circularize when they're less than a certain eccentricity coming in. So this is a plot of the spectrum, the FFT of those waveforms versus the frequency in code units of M, so we could scale it depending on what type of binary black hole system we want to look at. And you'll notice that early on, you can see all the interesting things present in the waveforms. But then in these higher frequencies, you see that things sort of latch on and they all follow the same curve. And in fact, there's a circular waveform in there as well. It's a red line, and you can't distinguish it in the late times. So some things are happening. First off, these are all eccentricities less than 0.4. And you can see on the plot from the right that the final spin of those black holes are all just about the same at about 0.7 up until you get an eccentricity of 0.4. And after 0.4, we're really transitioning to a plunge. So there's a couple things being compared there. You're going from having several cycles to you're really having one or two and plunging right into a single black hole. And then you can see that effect because you can see in the spectrum that they're all lying on that same ring down path to the same final black hole. So given this sort of viewpoint that for the mass ranges that we can cover looking at short cycles of gravitational waves, because this isn't a complete set of gravitational wave cycles coming from very far away, we asked the question, if you're going to assume that you only want to use circular waveforms to do detection of binary black holes, ignoring spin for now, how much could you get away with? And to do that, we assumed that the signal was our set of eccentric waveforms. From, in this case, I have here it was like, I think we started with a little less than 0.1 up to about 0.7. And we took as our template our circular waveform. So it was all pure numeric relativity waveforms, no post-Newtonian information was included. And we did the typical overlaps and fitting factors, right? So we're just comparing these waveforms, doing a mini-max thing where we sort of do the worst case scenario of the phases of the two waveforms, and we do a maximization over the mass of the template. And what happens is that, let's start with the high mass case. The higher the total mass, the easier it was to do this detection because you're really focusing on that last big bang, the merger and the rain down. The lower the mass, the harder the problem is, even though we only went to 60 solar masses because we didn't have too many cycles in our waveform. It gets much harder here because you're really covering more of that in spiral, where you had more modulation of the signal before it comes to all be the same final black hole mass. The other thing to notice here is you get this really big dip. We'll ignore this one for a second. Big dip at about 0.45. That line is our transition from in spiral to plunge. So definitely something happens there that's affecting the matches, because we get that big difference in comparing them to a circular template. The lowest mass case is really what's been holding us up. In finishing this work, you can see we actually went in and are doing a few more runs here. But that case is very difficult to compare with a circular template. So you could get away, I think, with quite a lot at eccentricities that are lower than about 0.2. And higher than that, it gets a little bit difficult, even in these high mass things that are really focusing more on the merger and ring down of the signal. We did a quick little estimate of what kind of mass bias, because we maximized over that mass of the template. We didn't assume they were the same, so we just wanted to ask the question, if we were doing that, how wrong would we be? And we got about 15 to 20%. The two lines of, I think looking above 0.4 is really unreasonable, and I certainly don't think we expect such high eccentric binaries anyway. I just included that for completeness. So you see that we get mass errors about 15% by assuming it's a circular template instead of an eccentric one. For fun, today, my old student who's now a postdoc did the same thing for an advanced LIGO curve. So all that was for initial LIGO. This is for advanced LIGO. We cut off at 0.4, and you see a very similar pattern. And these masses I haven't written yet, but this is, again, 60 solar masses, and that goes up to about 240. And that's the pattern we see for these fitting factors. So the last thing I'll talk about this eccentricity thing is we also just compared the signal to noise ratio, where they're normalized that the signal to noise for a circular template was 1, so we could compare them. And I'm bringing this up because I want to compare it to a result I'm going to show later from Laura's group at the University of Massachusetts, that we do see, with the caveat that I wouldn't take this 30% as being this important number, but we do see that you get sort of a further distance reach with the eccentric templates than we saw with the circular templates. But what numbers they are, by here, by 0.45, you're really just plunging, so a little difficult to compare them all. And on the right of the axis was the total mass of the binary again, so going from about 50 solar masses up to 200 in this case. And the different contours were different levels of comparing the two signal to noise, where you've normalized it to that circular template. So you get a little bit further with that eccentric case. We did a second test actually quite a while ago, a couple years ago, because it was really hard when we first started getting these binary black hole mergers to work to not want to play a little bit with its impact on data analysis. So even though the waveforms from this work in 2007 were really calculated so we could check gravitational recoil. Remember that, how we had a lot of fun for like a year or two doing gravitational recoil of binary black hole work. This is one of the first papers on the spinning case. And you can see from that waveform it's really short. So we're not talking a lot of gravitational wave cycles. And you can really see that junk radiation at about 50 M. But we went and took this scenario where the two spins were up and down, and they were equal mass and circular. And we started just looking at what would happen if you did attempt to use them to do some matched filtering. And this is a plot of the spectrum versus frequency for the different spin magnitudes. The spins have equal magnitude, just pointing in opposite directions from 0 to 0.8, where we see here at the theta equals 0 plot, that's if we were looking directly down at the plane of the binary. That means that only the 2-2 mode, the dominant harmonic, is important in the waveform. And as you go off axis, as you come away from that theta equals 0 point, the modes mix. And you can see the way that changes the spectrum. But so for your 0 spin case, 2-2 is the only thing you need, right? Completely dominant. Even for these guys, even though we have spin, it's still a very symmetric case, and you don't really need the higher modes that much. But without them, if we didn't include the higher modes in this very early paper written by my student Deirdre, you can see that the matches were ridiculous. This is 0.98, that's 0.99. There was just no difference between these spinning things. Okay, they're only up and down. This isn't the case where you have precession and stuff like that. So they are the closest to circular you could have. We're matching a circular case, a spin of 0. So a circular equal mass, non-spinning, numerical relativity waveform of the same quality as the rest, versus a series of different spin magnitudes. And everything was just 2-2 mode. So we didn't allow the higher harmonics to come in at all. And it was just, silly. So then we thought, okay, so this was really us learning, right, about how these things were going to play. And so then we allowed the higher modes to come in, and the way we did that was to allow the orientation to vary. So it's not that we're all of a sudden adding 3-3, or 4-4 in. Instead, the modes get mixed as you go off that theta equals 0 line. It's the same exact plot on the upper right, except now we're taking only 100 mass, solar mass case versus theta for the different spins, and once again comparing a no-spin waveform with a spinning waveform. And not surprisingly, the higher the spin, two things happen. One, the resolution gets a little low, so there should be error bars on that of about 0.1. And 0.05. And 2, you do see that, of course, the further you are away from that dominant mode, the more important become the contributions of the non-dominant harmonics. So one of the reasons why I said I was interested early in looking at the parameter space exploration for these merging type signals is that you could kind of imagine, now I don't expect that you guys in LC are going to go out and use these, but you can see that by just moving away from a a non-spinning waveform at a certain non-zero angle, which is the way I did all these comparisons, and instead do the matches with a spin magnitude of 0.4 and try to compare with all the different cases of spin, you can get a little bit better range of your spins. This case is a really minor one because you don't have precession and other things that are going to cause my simple criteria to be deviated from, but I just thought it was an interesting example of the way these waveforms might play out in detection. So the contours here are of different matches. So here's your 0.99 up to 0.96 match, and versus the spin and the total mass again on the left. So you just get a little more coverage out to the higher magnitudes by using 0.4, but you still do a pretty good job at seeing the non-spinning case for these pretty much plunging merger waveforms. Oops. So recently, really recently, about a couple months ago, Laura Codinati and I started talking about, well, what if we took some of these waveforms and try to use them in burst analysis? She was also part of NINJA, where she was using her burst analysis there. Now, I don't really understand exactly what's going on. People here in science probably understand the burst algorithm she's using better than me, so I'm not going to pretend. But this is what our goal is. We want to understand with a systematic study of how the parameters we're using, such as the spin magnitudes, the eccentricities, things like that, it can affect the detectability and parameter estimation in a burst search. And we're focusing on places where merger and ring down yield the most signal-to-noise ratio, where it's appropriate to ask this question. It's really a work in progress, and we really mean that because we've barely gone back and forth once or twice over what waveforms I've sent and what she's done with them. And what we did was we took the runs I already had that I just showed you, so the two sets that I just did match filtering with, she did with the burst, but now I'm doing new runs for her, so we can do a more systematic study. And what she's doing is she's testing the detectability of these mergers using simulated Gaussian noise with the initial LIGO design sensitivity. She set the SNR to 5.5, and she's using the Omega burst search algorithm developed in the LSE. That I obviously read. Right. Okay, burst searches. So she's searching for, the way that I picture this in my head is that it's basically match templates for sine Gaussians. I don't know how accurate that is, but that's the way I look at it. So she's searching for these gravitational wave transients without the assumption of what the waveform looks like. And she's using the numeric relativity waveforms as simulated signal. Once again, putting them in the role of this is what nature's doing. Now let's see what these sine Gaussians are going to see. And how far out are they going to make that detection at an SNR of 5.5. Right now we've only tested spin magnitudes and eccentricity using this Omega algorithm, and she chose a mass range of 80 to 350 solar masses. Once again, on the very high side because of the numbers of cycles in our waveforms and wanting the merger and ring down to dominate. Here's a plot she produced of frequency versus total mass. So a time frequency plot. And this is what was found. So the excess power happened in these frequencies, and they fit nicely between the ring down, which is the blue, and the ISCO frequency, which is red, which she expected. These guys up here are because they're outside of the mass range she was looking at. So these are just picking up higher harmonics. These were for the spin magnitudes up and down, the spin case I just showed you. So in general, what we started with were the eccentric waveforms, because we had submitted them to Ninja, so I submitted them to her to play with. And what she finds is when she looks at the efficiency curves of the 800 to 200 solar mass case and a 200 to 300 solar mass case, and she plots the fraction of signals detected at this SNR of 5.5, and intriguingly, she gets a little bit of a difference. So for the zero eccentricity case, she sees out 2.224 if she wants the 50% of the signals detected, and 66 megaparsecs if you want 90% of the signals detected, and a little bit less for the 0.2 case. A little bit more for the 0.2 eccentricity case. So they're up to 294 megaparsecs at the 50% count and 88 at 90%. Similarly, for the higher mass case, a same pattern emerges. So this is pretty preliminary. We only tried it with 2 different waveforms, but it kind of follows what we saw with our signal-to-noise comparison, which makes sense. You can see a little further with the eccentric case than with the circular. And there's the LSC document for reference. It's on this page as well. We very quickly have done a spin magnitude, the same up and down spins that I told you about a little while ago in the same procedure. And there was an error in the strain that was off by a factor, so the distances don't make much sense. But she's finding that the spin magnitudes do not matter, but neither does the harmonics. So the details that I saw from the matching, where we could break the degeneracy by including higher harmonics, is not making any difference for her SNR. So she sees them at the same distance, just using a circular case with 2-2 mode or including all the others for this kind of tiny case. So for fun, mostly, I was going to look a little bit beyond these cases that we're pretty sure exist in the universe and start playing with some things that maybe do, maybe don't. So this was a paper by Bensi Kostas and collaborators where they were seeing gravitational waves potentially emitted in parabolic encounters in stellar masses of black holes. Now I include the plot to the right as a sort of sobriety test, right? Okay, so we're not talking about large detection rates. In fact, for advanced LIGO, you're getting at, 0.01. So this isn't something to go out and code up. But there has been other works coming out recently that potentially advanced LIGO would see between 1 to 1,000 per year. Now, I don't know how likely that is, but we happen to have done some scattering hyperbolic type evolutions, and so we're considering looking in that direction. These are trajectory plots from a series of 6 different simulations. And what's happening here is they're not spinning and they're equal mass, but they're actually at 22 degrees off of the orbital plane, and we're just giving them a lot of momentum. So what's changing from A to F is the amount of momentum that we've given these 2 black holes. So they're not on circular orbits at all. They're on trajectories that either plunge like they do in A or go in and out. So they go from far away, they come in, burst a bit, and go back out again before they finally merge. And this was the scenarios that we used to actually get a ridiculously large recoil velocity in a recent paper, up to 10,000 kilometers per second if you actually use spinning black holes of 0.8 instead of the non-spinning black holes. So that's just to put it in perspective that these black holes just love to get kicked out of galaxies if they actually existed. We also looked at this case for the final spin. So this is the same trajectory series here. This figure is for the non-spinning case, initially non-spinning black holes. And we found that there was a peak spin you could get that's significantly less than the Kerr limit. So we could only go up to a little bit less than 0.8. And we can't surpass that no matter how much linear momentum we pumped into the system. Okay, so we got a peak of about 0.8 final spin for any of these cases that we tried, and the peak is coming at an L almost equal to mh squared, just about at 1. So one of the things I think is interesting about these scattering encounters is their bursty behavior. Franz Pretorius, I think, saw things like this as well. He was looking at zoom whirls. So this is D, E, and F from that trajectory plot, and you can see that because they come in, zoom a little bit, whirl a little bit and zoom back out again, you get repeated bursts. So here's one before it merges. And we are intrigued in thinking about using these to see if they might be interested in as a burst analysis. So my conclusions. You guys are really quiet. I'm used to people stopping me like 30 times, but I'll take it. So right now, there's a lot of work both at the individual and community level to see if we can take some of this information from numerical relativity and work it back into gravitational wave analysis. I think that there's some chance that since we really only have a very limited partial coverage of the parameter space right now, it's a little daunting to think about going everywhere, but maybe we can find these tracks in the space where you can use a limited number of templates to detect a bunch of them. We're currently evolving waveforms of generic spin orientations for much longer than our original ones, at about 8 to 10 orbits. And of course, adding some eccentricity and unequal masses, but there's only a certain finite number of them you can produce in a limited amount of time. So we've done some work with our eccentric templates and trying to make connections with data analysis in there, and started a new collaboration with Laura to look at their use for burst analysis and testing that burst algorithm. And of course, I still like the idea of looking at the unexpected, such as these crazy bursts that I showed in the end, and the zoom whirl behavior we see in hyperbolic encounters. And I just left that future role as sort of something to be thinking about. Thanks.